This slide shows a diagram that you saw in the last module when we were talking about behaviorism. And recall that behaviorism was sometimes referred to as black box psychology. The organism is this black box. You can't see what's going on in there. But behaviorists believe you really didn't need to worry about that because you could perfectly well predict and control behavior by understanding its relationship to the stimuli that were coming in from the world. In this module, we're going to look into the black box and understand how we process information, how we store that information, and how we retrieve it at a later point to make use of it. In this PowerPoint set of slides, we're going to focus on the process of perception. So if you look at the diagram, the arrow coming in from the left that says input or stimulus. How do we capture this sensory stuff out there in the world, light waves, sound waves, and turn it into meaningful information that we store and retrieve later on? In daily life, perception is almost always a combination of sensory input from the world and our cognitive expectations about what we ought to be perceiving out there in the world. And therefore, we're going to make a distinction between something called bottom-up processing, also known as data-driven processing, and top-down processing, also known as conceptually driven processing. Let me give you a silly example to illustrate the difference. Let's suppose instead of being in an online situation this term, you were at Knox and having an actual class with me and the other students all together in the same room on a regular schedule. Let's suppose after class one day, it was a nice sunny day, and I said, hey, you want to go for a ride in the country? Now, setting aside for the moment that this would come across as a bit creepy, and you probably would run the other way, pretend that you came along for the ride. So we're driving around in the countryside outside of Galesburg, and off in the distance we see a farm. And on that farm you see some large, dark shapes moving around, but they're too far away for you to very clearly tell what it is. However, you're already scanning the environment because you expect certain things to be there. So large things that are moving around, if they're on a farm, are likely to be cows or horses or hogs. And so you have a set of expectations about what you ought to see there. And this helps you recognize ambiguous stimuli more quickly. That is, if in fact the thing that's out there is what you expect to see. If, on the other hand, it was some other kind of animal, a tiger or something that doesn't belong on a farm, it might actually take you longer to recognize it because you're searching around in that part of your memory where only animals that are found on farms are located. Now, bottom-up processing depends entirely on the sensory information you're receiving from the world. You don't have any expectations at all. So instead of going for a ride with me of your own accord, imagine that you're filing out of the classroom at the end of class, and you happen to be the last person leaving the room, and I sneak up behind you with a handkerchief full of chloroform and put it over your face until you're unconscious. And then I drag you out and throw you in the trunk of my car. And I leave you there until it's nighttime. And then we go out for a drive in the countryside. Now, imagine that there's a small hole in the trunk of the car where you can look out. And you have no idea where you are, and it's dark. You can't see anything. And suddenly you notice some dark shapes moving in the distance. And you look at them intently to try to figure out what those are. But you don't know that you're looking at a farm, and therefore you don't have any context at all to guide your expectations. So in this situation, you don't have any top-down processing going on. You only have bottom-up processing. You're processing data from the world until you have enough of it to decide what it is you are perceiving. This is a pretty rare situation in real life. Most of the time, you have both data from the world and a context or conceptually driven processing going on. Context effects are things that help you recognize objects because they initiate top-down processing. For example, if you look at these two words, the cat, you'll notice that the middle letter in each word is exactly the same. However, in the first word, you immediately see it as an H because it's surrounded by the T and the E, and they create a context that leads you to expect an H there. The other word, however, has the same letter, but it's surrounded by a C and a T, and you immediately recognize that as an A for cat. In each case, your recognition of the middle letter is driven by the context of the letters around it. And this kind of thing happens to us in different contexts all the time, right? If you are in my class and I show up at the classroom and I see your face, I immediately recognize you and know who you are because in that context, I expect to see Knox students and specifically you. On the other hand, let's suppose we both independently of each other go to a mall in Peoria on a weekend. And I'm walking around in the mall and you go walking by me and I look at you and I show no sign of recognition. Well, the problem here is I'm seeing you out of context and I don't have a set of expectations driving the identification of faces. Now, if I know you well, obviously I'm going to recognize you, but if I just know you sort of casually, being in my classroom provides a context that helps me recognize you. Psychologists who study perception have come at it from many different directions. One way is by using something called a probabilistic model. According to probabilistic models of perception, we don't passively receive information from the world. What we do is actively sort through, distort, recombine, change information, and basically we create and build a perception from the raw material that the world provides for us. From this perspective, the world is a kind of confusing place, and you wouldn't be able to make sense of it if you didn't do something to organize it, get rid of some stuff, recombine other things. And they're called probabilistic models because what we're essentially doing when we perceive something is make a judgment about what's probably out there. So we're making a prediction about what information this confusing stuff coming in is giving to us. On the other hand, there's a school of thought called ecological models that say that, in fact, we can trust sensory information and that there is no need to distort it. The information the world gives us is reliable in and of itself, and we don't really need to do anything about it. So if I'm in this camp, I will say that survival wouldn't be possible in a world of probable stimuli. If I'm looking both ways before I cross the street, I need to know if a car is coming or not. If I'm just making a judgment that probably there's no car coming, pretty soon I'm going to be removed from the gene pool. And so, according to ecological models, that sensory information I'm getting from the world can be trusted. If I don't see a car coming, that means there is not a car coming. Now, there's information and data out there to support both ways of looking at this. There is information supportive of the probabilistic point of view that we do change sensory information and construct things. There's also evidence in favor of ecological models. I'm not going to try to resolve that dispute right now, but I do want you to be aware that there are different opinions about how we handle sensory information. I'm going to rely more. So the Gestalt psychologists have developed a series of rules that we use. We follow these rules to help us impose order on the world around us. One of the first decisions we have to make when we're perceiving anything is to make a distinction between figure and background. So we have to distinguish figure from ground. For example, if I'm having a conversation with you and we're in a very crowded room with a lot of other people talking and there's music playing in the background, I need to filter out the background music and all of those other voices and focus on your voice so I can have a conversation with you. So in this situation, your voice is the figure. The other stuff, that I'm distinguishing it from is the background. Or when you're driving your car down the street, there are certain things you need to distinguish from everything else. You have to see if there are any pedestrians crossing the street so you don't run over them. You have to see what the other cars are doing so you don't crash into them. You have to be on the alert for stop signs and traffic signals. The other non-relevant stuff, like the mountains in the distance and the clouds in the sky, you need to filter out to distinguish the important stuff in the foreground, the figures, from the less important stuff in the background, the ground. Most of the time, this is fairly easy to do, but psychologists do sometimes study perception by looking at what are called reversible figures. These are figures where the cues that we usually use to distinguish figure from ground are missing, and therefore we can flip-flop back and forth and see the perceptual field in two different ways. And eventually we figure out which thing we think is the figure and which stuff we think is the background. And then whenever we see the slide or the picture after that, we will tend to see it that same way. And this is called figural persistence. Once we've decided what the figure is, that's what we will see first. Now you can still kind of flip-flop back and forth and see it both ways, but you can't see both ways at the same time. I'm going to show you some slides with what we call reversible figures in a moment. But there are a number of things we do to help us figure out what the figure is. We use the principle of proximity to group things together that are close together. So if things are close together, we'll tend to perceive them as part of the same figure. We group similar things together. So you're going to see some slides where I give you some examples of the grouping principle of similarity. We tend to see symmetrical things as being figures. We see continuous things as being figures. We see things that are closed and separate from the rest of the field as figures as well. And once we see things a certain way, once we have decided what our perception is, we tend to keep that constant. And this is called a perceptual constancy. So there are brightness constancies, size constancies, color constancies, and so on. So for example, if I'm talking to you in a hallway and you start walking away, the image that you cast on my retina gets smaller, but I don't start freaking out and screaming, you're shrinking, because I have decided how big you are, and the fact that your image on my retina has changed doesn't cause me to perceive you as being smaller, even though it probably should, because the image that I'm receiving from the world is that you are smaller. Similarly, color is something that depends very much on the quality of the light. Color doesn't exist in the world. What we perceive are wavelengths of light, and color is then created in the brain. So if I change the lighting level in a room, the color of your shirt actually changes. But you don't perceive that because you have decided what color the shirt is, and you will then tend to perceive it because of perceptual constancy as being the same color after that. Let's take a look at some examples of all of these things that I just described. Here's an example of a reversible figure. Is this a set of white things against a black background, or a set of black things against a white background? It's really hard to tell. It could go either way. So continue to stare at this. And you'll see that it can suddenly jump from looking one way to looking completely different, because what you're doing is switching back and forth between seeing the black as the background or the white as the background. I'll let you look at this for a little while so you can have that experience. But once you've decided that it's white on black or black on white, forever after, whenever I show you this picture, you would tend to see it that way first because of figural persistence. This is a famous reversible figure that you probably have seen before in other places. It's sometimes called the Peter Paul goblet because, once again, you're trying to decide if it's a white thing against a black background or a black thing against a white background. If you think the background is black, you probably see a white vase or goblet or chalice. On the other hand, if you decide that the background is white, you probably see two faces looking at each other in profile. So I'll let you take a look at this for a moment. Hopefully you'll be able to see both of those things. When this slide first flashed on the screen, many of you immediately saw the goblet, and now you're having to work at trying to see the faces. Others of you saw the faces immediately and probably had to work at it a little bit to see the vase. For whatever reason, I have always seen the vase first. I can see the faces very easily when I look for them, but the first thing that pops out at me is the white vase. In this reversible figure, you probably see either a series of columns that look vaguely like chess pieces, or you see two pairs of people in conversation bending over towards each other, standing against a white background. I'll leave this on the screen for a little bit so you can flip-flop it back and forth and see both of those things. Here's another well-known reversible figure. When you look at this photograph, it's not actually a photograph. If you look at the picture, you can see either an ugly old hag or an attractive young woman, depending upon how you structure your perception. Now, this one is going to be harder for you to see the other way around. For those of you that see the young woman, let me explain how you would see the old hag. If you look at the photo, you'll see a very large nose, and that horizontal red stripe down below is a mouth in sort of a sad smile, and then there's a very protruding, strong chin underneath that. And above the nose, you see the eyes, and she's got sort of a scarf on her head with hair coming out the front. For those of you that only see the old hag, let me explain how you would see the young woman. Imagine that you're looking at a woman from the side, her left side, and she's turning away from you. So now that red stripe that was the mouth on the old hag is actually a necklace of some sort around the neck of the young woman, and you can see the curvature of her jaw with her left ear just above it. And on the far left side of the flesh-colored part, you can see the tip of her nose and an eyelash as she's looking off into the distance. So keep looking at that. Hopefully most of you will be able to see both of these things, but you tend to see one more easily than the other. I, for example, always see the old hag first, especially when I go home from work at the end of the day. Oh God, I should change this slide. Here's another reversible figure. You may see what looks like the statue of a head perched on a neck with long black hair, looking off to the left. Or you might see what looks like an Eskimo wearing a parka, looking at him from behind as he stares into a dark cave. In this reversible figure, do you see a duck or do you see a rabbit? This figure is known as a reversible cube. All I can really do is ask you to stare at it. And if you stare at it long enough, you'll suddenly see it flip-flop and jump into a completely different configuration. If we were in the classroom together, I like listening to the ahas and the gasps when people see it. There's this, I kind of miss that when you guys are looking at this all on your own. This figure is sort of like the reversible cube you just saw, except this is a reversible stairway. Stare right at this. Just keep looking at it sort of right in the center of it. And if you stare at it long enough, you'll suddenly see it sort of turn itself upside down. And then flip itself right side up again. And as you continue to look at it, you'll see it go both ways. This one's a little tricky. How many circles do you see? I won't say any more about this. I'll just let you keep looking at it until you see what it's all about. Let's return to the Gestalt principles of grouping that help us figure out what are figures and what are backgrounds. If you look at the dots in the left of the picture, you'll see rows of blue dots and rows of black dots. And that's probably how you will describe it to people. If you just ask somebody, tell me what you see in that picture, most people will report that they see blue dots and black dots. They group things together according to similarity. Most people will not say, I saw 5 columns of dots, or that I saw 20 dots. They put things together by lumping things that are the same into categories. So this is blue dots and black dots. In the next figure over, if you ask people what they see there, most individuals will say, I see 3 pairs of lines. So you group the lines that are closest together as one figure. So we group things according to their proximity to each other. The next diagram over will lead you to perceive a relationship between the dots that seem to form a more or less continuous line. And so we'll tend to see them together as part of a figure. In the last picture, you'll see most people will describe a circle and a square with pieces missing. But if the pieces are missing, then it's not a circle and it's not a square. But we like closure. We sort of fill in the gaps. Sometimes you can have fun with people by presenting them with stimuli where these different principles conflict with each other. So, for example, if I were to give you an image that would lead you to see it one way if you were using proximity as the principle, but see it a different way if you were using similarity, you would see people getting confused and not sure what they're looking at. There's a link on this screen, but you can also see the link on the webpage for this module, and it's entitled The Optical Illusion Dance. It's an interesting and fun clip of a group of girls dancing, but they're dressed a certain way, and the conflicting information you're getting mess with your Gestalt principles of grouping and lead you to see it in a very bizarre way. I definitely recommend you take a look at it because it's fun. On this slide, the principle of proximity leads us to perceive a Dalmatian just by the pattern of how the black spots are located. And there is no outline for the dog's body. We kind of draw that in our own mind because the principle of proximity leads us to believe it's a dog, and so we fill in the missing spaces. Similarly, most individuals looking at this will perceive a white triangle laying on top of other things, and so the white triangle appears to be covering up parts of the black circles and parts of the black triangle. But in fact, there is nothing there. There is no white triangle. That's just an absence of any ink at all. But we create this boundary around that space that lead us to see it as a figure because the principle of closure leads us to do that. This slide illustrates the principle of size constancy. The figure of the man in each of these pictures is exactly the same size. And he's exactly the size as that blue line that you see out to the left of the photographs. But we perceive the man as being much bigger in the one picture than we do in the other picture because the other cues in the scene lead us to believe he's farther away. And because we think he's farther away and the image that he casts on our retina is exactly the same size, then we realize that he must be farther away. But it's the very same size in both pictures. When I show this on a screen in my classroom, I actually bring a yardstick in because students are skeptical of this, and I have to hold the yardstick up to the two pictures and show them that the guy is exactly the same size. This is the famous spiral illusion. At first glance, it appears to be a continuous single line that just goes around and around and around and forming a spiral. But in fact, this picture shows you a series of concentric circles. You can actually put your finger on one of those and trace it all the way around. So it's a circle inside of a circle inside of a circle. But the other cues that we're receiving mess with our Gestalt principles of organization and lead us to force ourselves to see a continuous line rather than concentric circles. I'm sure you've all seen pictures like this where you see the face of a famous person embedded in the scene. I won't say any more about this. If you don't see anything, try moving away from the screen a little bit. Sometimes you can see it better if you're a little further away. There's another famous one of these where the face of Einstein turns into the face of Marilyn Monroe. One toy that's been developed by a guy named Ames is something called the Ames Room. You may have seen these in children's museums in one place or another, where you have these three guys that appear to be very different from each other in size, but in fact, it's the room that's different. The guy that appears to be really small is actually a lot farther away from you than the guy who appears to be really tall. But the room has been distorted and creates expectations to you about how big things should be that you see in there. There's a video attached to this module that explains how the Ames Room works. I recommend that you take a look at it. Here's another picture of the Ames Room, showing you a picture of a teacher with his class, and you'll notice the teacher looks to be a lot smaller than most of his grade school students. And here's yet another picture of an Ames Room. And this diagram tells you something about how the Ames Room is laid out. This is the famous Ames window illusion. It's an illusion you can only see when the thing is moving, so you're going to need to look at a video of this. If you click on the picture on this slide, you should be taken to a video of the Ames window in operation, along with an explanation for how it occurs. But on the web page that goes along with the module for this module for the course, you'll also see a link to the Ames window illusion. There are a lot of other famous illusions that you're probably familiar with. One is called the moon illusion. You've probably all noticed that sometimes the moon looks absolutely gigantic. You stop and you look at it and you say, wow, look how big the moon is. But if you go back and look at it half an hour later, it's gone. It looks completely different and it looks much smaller. We don't know all of the reasons why the moon illusion occurs, but one of them almost certainly is that when the moon is very low in the sky near the horizon, you actually can compare it directly with things like buildings and trees and get a sense of how large the moon really is. When the moon is higher in the sky, on the other hand, you lose that kind of contrast and it's harder to see the moon illusion. And here's another perspective on the moon illusion. And there are all kinds of size illusions that psychologists use to illustrate this principle. The three figures you see in this picture are all exactly the same size. It's just that the cues, other cues in the situation, the context cues, lead you to expect things to be either closer to you or farther away. And we adjust our perception of the size of the figures in order to meet those expectations. Here's another example of the size illusion that tricks us because of the context cues. The two monsters you see in the picture are exactly the same size. But because one of them looks to be farther away, we perceive it to be larger. There are also illusions of motion. This illusion is known as the rotating snakes illusion. Most of you, if you continue to look at this, ought to see things moving. But in fact, there is nothing in this picture that is moving. The picture is perfectly still and constant. The motion is entirely being created by your own perceptual processes. The motion is completely in your mind, not in the world. This is another illusion of motion. There is no motion going on in this picture at all, but many of you probably do detect that it's moving, especially if you don't stare directly at it. Move your eyes just a little bit up near the top, looking over the top of it, and you'll perceive the motion even more clearly. One of the most famous illusions of motion is known as the phi phenomenon. In this picture, you see what appears to be movement going around and around and around in a circle, but it's really just little circles blinking off and blinking back on. But the sequence within which they do that leads us to perceive motion, where none actually exists. And yet another visual stimulus that leads us to perceive motion where none exists. We also tend to see spirals here, but again, these are concentric circles that you can trace with your finger. So not only do you see motion where none exists, you see shapes that are different than what actually exists. Impossible figures are pictures of objects that mess with your mind by giving you conflicting cues about what the thing looks like. So your expectations about how the world operates crash head-on into the sensory information you're actually perceiving. This one will drive you crazy if you look at it long enough. This is the famous Mueller-Lyer illusion. The two lines are exactly the same length, but one of them appears to be shorter than the other just because of the way that they're capped off with different arrow-like things at the end. One of them makes the line seem a lot shorter than the other. There's a famous artist whose last name is Escher, who's had a lot of fun with this kind of drawing, where he draws impossible figures. This one is called the Eternal Staircase. Just follow the path going up the stairs and up, and it seems like they go up forever. Similarly, follow the path of the water in this photo or picture. Another impossible figure. Some illusions have a much more straightforward biological basis. For example, I want you to just keep staring at the slide of this flag. Just keep staring at it. Try not to blink. Just keep looking at it. I don't care if your eyeballs are getting so dry that you feel like they're going to roll out of your head. Just keep staring at it. A little bit longer. Keep looking at it. Now, what do you see? Many of you probably immediately saw a red, white, and blue American flag against this white background. If you didn't see it this time, go back and look at the slides again and stare at the flag a little bit longer. But what happens here is that structures in the eye that are known as the cones get fatigued when you keep staring at the same color over and over again. And when you remove the stimuli, those cones shut down and the opposite member of the pair kind of is triggered, and you see the complementary color. We'll talk about that a little bit starting with the next slide. So I do want to say a few words about color vision. I don't want to get too bogged down in it, but you'll be reading a little bit about this in some of the assigned pages for this module. But I'll make it as simple as I can. When we're seeing color, there are certain things in the retina of the eye that are responsible for letting us do that, and those are called cones. Other structures in the eye that detect variations in light are called rods. Rods allow you to see black, white, shades of gray, and if you only have rods, the world would look like a black and white movie. And there are people who do only have rods. It's pretty rare. They're called rod monocrats, but they can't see color at all. People who are colorblind, on the other hand, usually have a specific kind of color blindness. There are two different kinds of pairs of cones. There's the red-green pair and the blue-yellow pair. And if you have red-green color blindness, which is the most common kind, you can't distinguish reds from greens. They all look the same to you. If you have blue-yellow color blindness, on the other hand, you can't distinguish blue from yellows. Color blindness is a sex-linked trait, so it's much more common in males than in females. Tests for color blindness present you with stimuli that you ought to be able to perceive as figures against a background of a different color. But if you are red-green colorblind, you may have trouble distinguishing any kind of figure in this mass of little circles. Those of you who are not colorblind ought to see a green number 7, or perhaps it looks like a question mark to you, embedded against a red background. Here's one that may look a little more clear to you. Again, this is for red-green color blindness. And here's one for color blindness as well. And this should be the clearest example of all. A person with red-green color blindness would not see the words page 5 in here at all. They would just see a mass of colors or a mass of circles that all look to be about the same color. This slide depicts what this picture of apples might look like to a person who's colorblind versus not colorblind. I had a friend in high school who was red-green colorblind. Oddly enough, he went on to college to become an art major. But I remember learning about this one day. There was some club in my high school that used to make money by selling bright red, shiny candied apples. And so you could buy these candied apples in the cafeteria at lunch on certain days. Well, on St. Patrick's Day one year, they sold bright green candied apples instead of bright red candied apples. But this guy could not tell the difference between them. And I thought that that was absolutely fascinating, that to him, this bright red thing and this bright green thing looked exactly the same, when to me, they could not have been more different. And here's a slide that shows how this hot air balloon might look to a person with red-green color blindness. The one on the left is what it would look like to a person who was not colorblind. The ones in the center and in the far right would be the colorblind versions.